Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering a whole new topic called cross-site scripting, or in short, XSS. Let's get started. First, we're going to discuss the technical details behind cross-site scripting vulnerabilities. So what is a cross-site scripting vulnerability? What are the different types of cross-site scripting vulnerabilities? How common and critical are these types of vulnerabilities, and so on. Next, we're going to cover how to find and exploit XSS vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing the application to determine if it's vulnerable? In this section, we'll go over XSS vulnerabilities of varying difficulty levels and how to exploit them. And we'll even discuss how to bypass certain defenses that are put in place by developers. Last but not least, we'll cover the different techniques that can be used to prevent or mitigate cross-site scripting vulnerabilities. Okay, let's get started with the first section, which is what is a cross-site scripting vulnerability. Cross-site scripting, or in short XSS, is a vulnerability that allows an attacker to inject malicious code or client-side scripts in the application that ends up getting executed in the web browser of the victim user. So unlike SQL injection or command injection, cross-site scripting is a client-side vulnerability. When you exploit this type of vulnerability, you're not actually exploiting the application server. You're exploiting the users of the application. Let's take an example to better understand this. Imagine you have a banking application that allows you to choose the language of your preference. So you're given the option of either English or French. Now, when you select the language, what happens is that the application performs a request that takes in your language preference as input to a parameter in the URL. It changes the language, and your input gets reflected back in the client-side code. Now, this makes it a perfect recipe for cross-site scripting vulnerabilities. As an attacker, what I could do is visit the application and inject my malicious code in the language parameter. Now, since this gets reflected back in the source code of the application, then if there's no validation on this lang parameter, I could inject whatever code I want. So if you look over here at the example, the first thing that the attacker did is look at the application to see if there are any parameters in the application that accept client-supplied input, and that client-supplied input gets reflected back in the source code of the application. So it gets reflected back in the browser. And the attacker finds out that the lang parameter, which should really just have either English, so EN for English, or FR for French, the lang parameter was found to actually accept any string of characters. And so what the attacker does is that he constructs a malicious script, and then he hosts that malicious script on his server, so attackerserver.net, and then uses the vulnerable parameter to call that script and execute it in the banking application itself. Now, the issue over here is that if the attacker clicks on this link right over here, the attacker is executing the script in his own browser. So essentially, the attacker is exploiting himself. So with this type of cross-site scripting vulnerability, which is also known as reflected cross-site scripting, you need to phish the user, or you need to get the user to click on the link that contains the malicious code so that the malicious code runs in the browser of the victim user. So if we go back to our example over here, after the attacker has identified the vulnerable parameter and injected his malicious script in the vulnerable parameter, the attacker has to entice the victim user, which is Alice in this example, to click on the link. Now, when Alice receives the email that says, hey, you could perform your banking applications using this link over here, Alice is not stupid. She's gone through all the security trainings, and she knows that she needs to check the domain of the link. Now, Alice hovers over the link and sees that the domain is truly the domain of her banking application, which means that she should trust the link and click on the link to perform her banking operations. And that's essentially what she does. She clicks on the link, she gets directed to her legitimate banking website, and she performs all the banking application that she needs to perform. However, what's happening in the background is that this script right over here, so the malicious script, ends up executing in Alice's browser. It accesses Alice's cookie store for this application, steals Alice's session token, and sends it to the victim user. And that's essentially how cross-site scripting vulnerabilities work. The idea is you're injecting client-supplied input in the application that ends up getting run in the victim's browser and then potentially performing actions on the behalf of the victim, or even in worst case scenarios, compromising the victim's account. Now you might be thinking, this is such a long process. Why even exploit the cross-site scripting vulnerability? The attacker could just direct the user to the attacker-owned server, and when the user clicks on the link, it'll execute in the user's browser and steal all the user's session tokens, not just the session of the banking application. Well, that's not exactly how it works. Browsers abide by a rule called the same origin policy, or in short, SOP. This policy segregates content that is received from different origins or domains to prevent different domains from interfering with each other in the user's browser. So the browser does not let any random script that is running on a different domain from accessing the content and the responses of the application. The request has to be originating from the application itself, which is why for this attack to work, you absolutely need to be able to inject your malicious code in the application itself, just like we did over here. The malicious script is truly running on the legitimate application bank.com, and that's why it's able to access the content of the browser for this application and compromise the user's account. All right, hopefully we now have a proper understanding of how cross-site scripting vulnerabilities work. Let's move on to discuss the different types of cross-site scripting. There are 3 different types of cross-site scripting vulnerabilities. The first one is reflected XSS. The example that we saw was a type of reflected cross-site scripting vulnerability because the user's input was directly reflected back in the response of the request. Now, there are 2 other types of cross-site scripting vulnerabilities. The first one is stored XSS, and the second one is DOM-based XSS. Stored XSS is really similar to reflected XSS, with the exception that the malicious code gets stored in the application instead of directly reflected back in the response. This type of XSS is way more dangerous because you no longer need a phishing component to your attack. Let's take an example to better understand this. Imagine you have an application that allows you to post your review on products that you bought, and this review becomes available to everyone else that visits the page for that specific product. In this case, if the input is not validated in the backend, then the attacker could simply inject his malicious script in the comment field, post the comment, and this way anyone that visits the page, the malicious script ends up getting executed in their browser. So not only does stored XSS no longer require you to deliver the exploit to the victim user through a phishing link, but now you can also compromise a ton of users. Anyone that visits the page can be compromised. Now, there's a ton of stored XSS vulnerabilities that have been found in real-world applications, but a really famous example is the MySpace social networking site. In 2005, it was found to be vulnerable to a stored XSS vulnerability in the user profile page. So a user, or also an attacker called Sammy, he placed malicious JavaScript in his profile page so that anyone who visits his profile, the script executes, it adds Sammy as a friend, and it copies the content of the script in the victim user's profile page. This way, when anyone also visits the victim user's profile page, Sammy gets added as a friend, and then the malicious script gets also added in the other victim's user's profile page. This was essentially an XSS worm that spread across the entire social networking site to the point that MySpace had to be taken offline and they had to remove all the malicious scripts from all the victim users' profiles. So this is definitely something that you should look for. All right, that was stored cross-site scripting vulnerabilities. Let's move on to DOM-based cross-site scripting vulnerabilities. DOM-based XSS is a type of cross-site scripting attack where the attack payload is executed as a result of modifying the DOM environment of the victim user. For those of you that are not familiar with the DOM, DOM stands for Document Object Model, and it's essentially the programming interface or API for HTML and XML documents. The way it works is when you load a web page into the browser takes the HTML of the application and converts it to the DOM, and then any JavaScript in the application can access the DOM to dynamically change elements within the HTML document. Now, DOM-based XSS vulnerabilities, as the name suggests, occur when the JavaScript is taking in client-supplied input and passing it to what we call a sink, or a potentially dangerous function without any validation. To better understand how this works, let's go back to reflected cross-site scripting vulnerabilities and then compare them to DOM-based cross-site scripting vulnerabilities. In this example over here, the vulnerable request is a GET request, and it takes in a parameter message. Now, this parameter contains the message that you want to display to the user, and in this case, the message is all is well. So the content of the message parameter is inputted in a paragraph element in the HTML document and displayed to the user. This is the view that you would see if you right-click in your browser and then click on View Page Source. Now, if this message field has no validation whatsoever, then an attacker could simply inject a malicious script that alerts on the cookie of the user. Anything that you put in the message field gets added in the HTML paragraph element, and when the HTML document is rendered, the browser sees that this is a paragraph element and it contains the status string, and so it displays status to you as the user. However, when it gets to the script element over here, it sees that this is JavaScript, and so it essentially treats it as JS code, and it calls the alert function, and then in the alert function, it displays the content of the cookie of the application. So for you as a user, you'll see an application that contains the string status, but you'll also be alerted with a window that contains the content of your application cookie. And that's essentially how reflected cross-site scripting vulnerabilities work. Now, the key thing to understand over here is that the XSS payload was directly inserted in the HTML page itself and changed the content of the page. DOM-based XSS vulnerabilities work a little bit different. The page itself does not change, but the client-side code contained in the page executes differently based on the malicious input that you give it. In this example on the screen, you have a search functionality that allows you to search for items in an online store. Now, when you enter your input, it does not get directly reflected in the page, just like with reflected cross-site scripting. Instead, the application uses some JavaScript to read the value of the search field and then write the value to an element within the HTML document. Here, our sink would be the inner HTML property because it alters the content of the HTML page. And so if there's no validation on the client-supplied input, then it could potentially be vulnerable. The exploit would involve adding an image tag that when there's an error in loading it, it executes your malicious function. Now you might be thinking, why not use the script tag that we did in the previous example? And the answer is that according to the HTML5 specification, the script tag won't execute within the inner HTML property, so we had to get a little bit creative and use the image tag. But the takeaway over here is that DOM-based XSS attacks involve modifying the DOM environment of the victim user versus your input just getting reflected back in the page and modifying the HTML page itself, which is why they're a little bit more difficult to find and exploit. We'll look at more examples when we discuss how to find and exploit these types of vulnerabilities. All right, now that we have discussed the three different types of XSS vulnerabilities, let's talk about what you as an attacker can do when you identify that the application you're testing contains a cross-site scripting vulnerability. The first thing that you could do, and it's the first thing that most attackers would do, is see if they could impersonate or masquerade as the victim user. This attack vector usually involves stealing the session token of the user. Now, this is only possible if the session token is stored in an insecurely configured cookie, so a cookie that does not have the HTTP only flag set, or the session token is stored in insecure locations that are accessible by JavaScript, like local storage or session storage. Another thing you could do is carry out any action that the user is able to perform and read any data that the user is able to access. Since your malicious code is running in the application in the user's browser, you're essentially able to perform any action that the user can perform in the application. You could also inject Trojan functionality into the application that models the login functionality of the application and tricks the user into inputting their credentials. To make the attack even more sophisticated, you could actually relay the credentials in the fake login functionality to the real login functionality so that the user logs into the application and doesn't understand that there's an attack that is happening. But what happens in the background is that you send the login credentials of the user to your attacker-controlled server and essentially compromise the user's account. You could also deface the application with inappropriate or politically motivated messages. So this is just a sample list of attack vectors that you can perform with XSS vulnerabilities. There's really an endless list of possibilities, which brings us to our next slide, covering the impact of XSS vulnerabilities. The impact of an XSS vulnerability largely depends on the type of XSS vulnerability that you identify in an application and the attack vector that you want to perform, so your goals and motives. We saw an example where an attacker wants to deface a website. In that case, integrity is heavily impacted. However, confidentiality and availability are not impacted. Now, in other cases where, let's say, you perform a full account compromise, it could impact all three: confidentiality, integrity, and availability. In fact, what attackers usually do is chain the XSS vulnerability with other vulnerabilities in the application to achieve a full account takeover or even remote code execution. A real-world example of that is the Magento application. Last year, it was found to have a critical vulnerability that involved exploiting a stored XSS vulnerability that can eventually lead to an arbitrary code execution, which tells us that when you chain the XSS vulnerability with other vulnerabilities in the application, or other functionality in the application that is usually only available to highly privileged users, it can have disastrous consequences. And that's why XSS now falls under the third most critical security risk facing web applications today. It used to have its own category in 2010, in 2013, and in 2017. However, right now it got looped into the injection category, which is the third most critical security risk facing web applications today. I've personally tested a ton of applications and I'm yet to find one application that does not have a cross-site scripting vulnerability in it. So these types of vulnerabilities are definitely still around and can lead to terrible consequences. Alright, so far we've learned the theory behind cross-site scripting vulnerabilities, and we looked at the three different types of XSS vulnerabilities. In this section, we're going to discuss how to find and exploit these types of vulnerabilities. Finding and exploiting XSS vulnerabilities varies slightly depending on the type of cross-site scripting vulnerability. So the way we're going to approach this section is we're going to discuss it based on each type, and we'll start off with reflected cross-site scripting vulnerabilities. The first thing that you want to do is identify every endpoint in the application where user-supplied data is reflected in the response. This includes parameters or other data within the URL query string, the URL file path, and even in some cases, HTTP headers. Now, the way you would do that is you would submit a unique arbitrary string that does not appear anywhere in the application and is unlikely to be affected by XSS-specific filters. The reason we do that is because we want to query the responses in the application to see if our unique string appears in them. An example string would be, let's say, test12564, which I just came up with, It's just a short string of alphanumeric characters, and it does not contain any tag names or special characters, and so it's quite unlikely to be blocked by any XSS filters that the application uses. Now, once you've entered this string in every endpoint of the application, then it's a matter of monitoring the application's responses for the appearance of that string. When you do find it in the response, that means you have found a location in the application where client-supplied input is reflected in the application. That in itself does not mean that it's vulnerable to XSS. However, it does mean that it definitely needs to be tested for reflected cross-site scripting vulnerabilities. So the next step would be to determine the reflection context. That's the syntactic context in which the data is reflected. So for example, is it reflected in a tag attribute, or maybe it's reflected in a script element, or even an attribute containing a URL? Depending on where it's reflected, the payload will be different. So it's important to understand the payload context, and then based on that, test your candidate payloads. We'll have a few examples in the next couple of slides that go over a few different contexts, and then based on those contexts, we'll build our payloads. Now, when you're testing your candidate payloads, chances are you're doing that using a tool like Burp Repeater. So it's always a good idea that when you do see your payload reflected and potentially vulnerable, you always should go back and test it in the browser to make sure that it is truly vulnerable. All right, let's look at a few reflected contexts and how you would build your payload based on each specific context. In the first example over here, the unique test string gets reflected in the value attribute of the input element. So you could see over here, this is my test string, which is test12564, and it's getting reflected in the value attribute of the input element. So in order for me to exploit this XSS vulnerability, I need a way to get out of the value attribute and even potentially get out of the input tag so that I could add my own malicious script. So the first payload that you could potentially use is the one in red right over here. The first thing that we're doing is adding a double quote so that we could close off the double quote for the string right over here. And then we're adding an angle bracket so that we could get out of the input element. And then it's just a matter of adding our malicious script, which just alerts a user with the integer 1. Note over here, we do have a trailing double quote and an angle bracket, which comes from right over here. But that's okay because the browser does its best to render a page even if there are some errors in the code. And so this is not going to break the application. So that's the first way you could exploit the vulnerability. Another payload you could use is the onFocus event, which gets triggered when you focus or click on an input element. In this case, you add a double quote again to close off this string right over here, but you stay in the input tag and you just add an onFocus event to run your malicious code. Note over here that we no longer have a trailing double quote and an angle bracket, so it's a cleaner payload, but it does require some user interaction in order for it to be triggered. So my preference would go to payload number 1. Another example is that your unique string is directly inserted in a quoted string within an existing script. So if you look over here, our string got inputted in some variable called a. So the way you would exploit that is to first close off the string using a single quote right over here. And then we add our own semicolon to end the initiation of that variable. And then we simply add our malicious code because we're already running in a script tag. And then we add a new variable called faux, which doesn't really do anything. It's just used so that we could close off the single quote that comes from over here to make sure that you don't introduce any errors that could potentially cause the script to run. Another example is the unique string gets added as part of the href attribute, which specifies the URL of the page. So you could see over here, my URL string is part of the href attribute. The way you would exploit that is use the JavaScript protocol to introduce the script directly within the URL attribute. Another way you could also exploit it is to simply get out of the href element by using the hash sign, which just denotes a page fragment and doesn't really go anywhere. And then you add the onClick event to run your malicious code. And that's essentially it. So with the three examples that we saw, each reflected context required a different payload, and so it's really important to understand the context in which your input is reflected before you start throwing random payloads at an input vector. Now, I do want to bring your attention to an amazing resource that is provided by the Portswigger organization. It's called the Cross-Site Scripting Cheat Sheet, and it essentially gives you all the different tags that you could potentially use and all the different event handlers that you could potentially use to create XSS payloads. And when you do select, let's say, a specific tag, it gives you the list of the payloads that you could use for that specific tag, and then it also tells you which browsers that payload would work on. It's an amazing resource that you'll see me use extensively in the lab videos, so I definitely recommend that you check it out, and I added the link on the screen right over here. I also have the link in the resources section. One thing that you might come across when pen testing applications is that there are certain filters or defense mechanisms that are put in place by developers to prevent cross-site scripting attacks. Now, depending on the defense that is put in place, you might be able to bypass it. So, for example, a certain defense would be that specific tags and even event handlers are blocked. In that case, the way you would approach it is you would use the XSS cheat sheet, which we just talked about in the previous slide, and run a brute force attack to determine which tags are allowed first, and then based on that specific tag, which event handlers are allowed and not blocked by the application. Another defense mechanism could be, let's say, no quotes of any kind are allowed in the input vector. In that case, you could use the from_char code function to return a string that is created from a sequence of UTF-16 code units. Over here, you could see that I'm just saying the word XSS, but in a real payload, it would be much bigger than that. But this allows you to bypass the fact that you need to use single quotes or double quotes. Another filter could be specific strings are not allowed. This can sometimes be bypassed by adding white spaces to break up keywords. This works because browsers can be a little bit lenient when it comes to white spaces in HTML and JavaScript. And so let's say the string JavaScript is not allowed. What you could do is simply add a tab in between the word to break up the word, and therefore it does not get picked up by the filter in the application. You could even use the encoded version of a tab. There's a ton more defense mechanism techniques that you could apply depending on how the application that you're testing functions. I've added a link to the OWASP XSS filter evasion cheat sheet if you're interested in learning more about the different evasion techniques. All right, we spent quite some time on how to find and exploit reflected XSS vulnerabilities, and that's okay because everything that we learned for reflected XSS vulnerabilities applies for finding stored XSS vulnerabilities. So the first step is the same. You need to identify every endpoint in the application where data is reflected in the response of the user. This again includes parameters in the URL, in the message body, in HTTP headers, and so on. Once you identify all the input vectors, you submit a unique arbitrary string that is not likely to be blocked by XSS filters. So again, we use the example of the string test12564. Now, the difference over here between stored XSS and reflected XSS is that with stored XSS vulnerabilities, the data entered in one location may be displayed in many locations in the application, which makes it a bit more cumbersome to find. So you would need to review all the application's content and functionality to identify any instances where the unique string is displayed back in the browser versus just reflected in the response of the exact request where you put the string. Now, once you do identify the instances, the steps are the same. You first need to determine the context, test candidate payloads in your proxy, and then confirm the attack in your browser. So everything that we learned for how to exploit reflected XSS vulnerabilities applies. It's just that the data is not directly reflected in the same response of the request. It might be reflected in multiple locations in the application. Okay, moving on to finding and exploiting DOM-based XSS vulnerabilities. This type of vulnerability is a bit harder to find. Since DOM-based XSS vulnerabilities occur when JavaScript is taking in client-supplied input and passing it to a sink, or what we said, a potentially dangerous function, Then the first step would be to review every piece of client-side JavaScript and identify instances where you have sinks or potentially dangerous functions that are used to access DOM data and can be controlled using client-supplied input. So example sinks would be document.write or document.writeLine or document.domain or element.inner HTML and so on. Now, once you identify the source that leads to a sink, then you add your unique arbitrary string and use the browser's developer tools to follow the path of execution to the sink. And then once you understand the path of execution, it's really just a matter of building your payload and testing it in the browser. In the upcoming videos, we'll be going over 30 labs that give you plenty of hands-on experience exploiting all three types of cross-site scripting vulnerabilities. So if you still feel like you don't understand a specific type of XSS or certain variations of a specific type of XSS, don't worry, you'll get plenty of hands-on experience when you actually exploit vulnerabilities in the lab environment. Of course, we can't end this section without mentioning web application vulnerability scanners, which are essentially automated tools that crawl your web application and look for vulnerabilities. I would say any decent scanner should have the ability to identify most reflected cross-site scripting vulnerabilities, just because the way you find them is a little bit easier than stored or DOM-based XSS vulnerabilities. Now, for stored or DOM-based XSS vulnerabilities, like I said, they're a bit harder to find, and so some scanners will report them, whereas others might miss them. So it's always a good idea to run a scan and then also perform a manual check to confirm that the scanner didn't miss anything. I personally use Burp Suite Pro Scanner, but there are so many other options ranging from open source to very expensive. So really, it's whatever you're comfortable with and whatever you're used to, and also the budget that the organization has to purchase such a scanner. All right, in the past couple of slides, we learned the technical details behind cross-site scripting vulnerabilities. We looked at the different types of XSS vulnerabilities, and then we learned how to find and exploit these types of vulnerabilities. In this section, we're going to discuss how to prevent or mitigate XSS vulnerabilities. The first and official defense to preventing cross-site scripting vulnerabilities is to encode any user-controllable data on output before it's displayed on the page. This ensures the user-supplied input is displayed safely as data versus as part of the client-side code. Now, this type of encoding you do is context-dependent. So depending on the technologies that you're using, you may need to apply multiple combinations of different encoding schemes. Let's say you're inserting client-supplied input within HTML. Then you will need HTML encoding. Whereas if you're inserting client-supplied input within JavaScript, then you need JavaScript encoding. So it really depends on the technologies that you're using and what this client-supplied input is interacting with. Now, just like with encryption algorithms, it's not recommended that you implement your own encoding library. And that's because chances are you're going to end up missing something and leave your application vulnerable to cross-site scripting vulnerabilities. So you really should always use an existing well-known library for the encoding mechanisms that you need and for the technologies that you're using. So if you go to the OWASP website, you'll see that there's a ton of libraries that are recommended depending on the languages that you're using for your application or the frameworks that you're using. Next, filter or validate input on arrival. This involves only accepting input based on what is expected or valid. For example, if you have an age field, then you should have a check in the backend that only accepts integers for that field. You definitely shouldn't be accepting alphabets. You should also not be accepting any other type of characters. Of course, when it comes to filtering input, using an allow list or a whitelist is much more secure than using a blacklist or a deny list. However, there will be situations where you're forced to use a deny list, and that's why filtering input on arrival is actually considered a defense in depth versus a complete defense against cross-site scripting vulnerabilities. Another defense in depth that you could perform is using the appropriate response headers. The content type and the X content type options headers indicate the format of the responses of your requests. So if you set them appropriately, an attacker would not be able to inject HTML or JavaScript in pages that don't have that specific format or what's also called as that specific mem type. Of course, this does not work on all pages because some pages do need to have HTML and JavaScript in them, and that's why this is also considered to be a defense in depth versus the official defense when it comes to preventing cross-site scripting vulnerabilities. Last but not least, you could use content security policy as a last line of defense. Content security policy is a browser security mechanism that restricts the resources that a page can load and restricts whether a page can be framed by other pages. So this helps in mitigating vulnerabilities like cross-site scripting vulnerabilities and clickjacking vulnerabilities. The way it works is that you set a response header called the content security policy header, and it contains one or more directives separated by semicolons, defining the policies and restrictions that you've set. In the example that we have set over here on the screen, the policy allows images, it allows scripts, AJAX, and CSS from the same origin and does not allow any other resources to load. So let's say if you're an attacker and you're loading a script from your attacker-controlled server, the content security policy header would not allow it because it's not coming from the same domain of the application. Of course, the setting that we have on the screen is a very strict configuration and it can be loosened up a bit based on your needs. I've got a link in the resources section that explains everything that you need to know about the content security policy. I definitely recommend that you check it out because this is a whole topic on its own that could take a full hour to explain, and we're not going to do that in this module. We do, however, have a few labs that involve the content security policy, so we'll get a little bit more in depth on that and understanding that when it comes to those labs. And that is it when it comes to XSS prevention. So the things that you absolutely should be doing is encoding any user controllable data on output and filtering input on arrival. But as defense in-depth mechanisms, you could also use the appropriate response headers to restrict the format of your responses, and then you could also use the content security policy header to restrict where scripts, images, and resources are loaded from in the application. All right, we've reached the end of our theory slides. I added links to a few resources in case you're interested in learning more about cross-site scripting vulnerabilities. The first link is the Web Security Academy page for cross-site scripting. So this is what this entire presentation is based on, so you should definitely check out this resource. The second link is the Web Application Hackers Handbook. If you have this book, check out chapter number 13, which discusses cross-site scripting. The Web Application Hackers Handbook was written by the same people that created the Web Security Academy, and so those two go kind of hand in hand, and I always reference them in any modules that I teach. The other links are mostly OWASP links, so the Open Worldwide Application Security Project. It contains a ton of resources for web security, and specifically for cross-site scripting, there's a few cheat sheets that you should be aware of. So the first one is the cross-site scripting prevention cheat sheet, which discusses how to prevent cross-site scripting vulnerabilities, and it goes down to language level. So if you're a developer, you might find this useful because if you're, let's say, coding in PHP, then there are resources specific to PHP. If you're coding in Java, there are specific resources in Java, and so on. The other cheat sheets are the OWASP XSS filter evasion cheat sheet, which discusses certain evasion techniques that you as a pen tester could use to bypass certain defenses that are put in place by the developers or certain defenses that are put in place by the web application firewall. And then you have the content security policy cheat sheet, which I discussed in the previous slide. There is one other resource over here that is not from OWASP. It's the cross-site scripting cheat sheet by Portswigger. Now, this cheat sheet is very useful, and the reason is because what it does is it essentially gives you all the different types of HTML tags that you could use in order to perform cross-site scripting vulnerabilities. And then for each tag, it tells you the events that you could use and the attributes that you could use. So you'll see me reference it quite a bit in the labs because I can't simply memorize every tag that could be used for XSS, and so I go to the cheat sheet, I select the tag that is allowed by, let's say, the firewall, or that is allowed by inadequate defenses that were put in place by the developers, and so on. And then based on that, I get my payload, and then I'm able to exploit the cross-site scripting vulnerability. So this is definitely a resource that we're going to be using quite a bit in the labs, and you'll also be using it in real-world penetration tests. And that is it for resources. Make sure to check them out if you're interested in learning more about cross-site scripting vulnerabilities.